In this section, we're going to be continuing discussing our double integrals, but now we're going to take a look at those integrals using polar coordinates. And in many cases, this will actually make the integration a little bit easier. So first thing I want to point out, something that I didn't really emphasize in the previous sections, is that when we're actually finding a double integral, we're integrating some function, a bunch of z values technically. So we integrate our z values, or add up a bunch of z values. And we add it up over this region in the xy plane, which I have kind of drawn in black there, upper left of the screen. And so what we're doing is we're technically taking our heights times the area of one of these little teeny tiny rectangles. We're letting these teeny tiny rectangles get infinitesimally small, and then we're adding them up. That's our kind of Riemann sum limit process, and that's technically what this integral is doing. So this dA stands for the area of one of these tiny rectangles created in this rectangular coordinate system. The area of a rectangle is length times width, and so the dA turns into a dx dy, and that's what happened when we did our double integrals in rectangular coordinates. So we would replace the dA with a dx dy, and again, that's representing area of one of those little tiny rectangles. Now, when we're working in polar coordinates, we're still adding up our z values over a region in the plane. But now we're thinking about this region in the plane in polar coordinates. And so when we do our kind of slicing, when we create our polar coordinate graph paper, we're thinking about regions based on the angle theta. So you can think of it as we're like slicing these kind of rays in the plane. And then we're also thinking about it based on a radius from the origin. And so that's what, maybe I'll erase my drawing. It's a little messier than what I have on the screen, but in kind of blue there, that's what that's trying to illustrate, is our region is being divided up based on angle and radius. And so we still have these tiny, oops, go back to that, tiny little segments here. So in our integral, we're going to be integrating our function, our z values. We'll write that as a function of r and theta. And then we're going to be multiplying that times dA. But in polar coordinates, the dA, the area of this tiny little segment, is going to be, and we're going to treat it like a rectangle because they're getting infinitesimally small. So the width would actually be dr, our change in radius right here is our width, but our length is technically an arc length. And arc length, write it over here, oops, arc length is defined to be radius times angle theta. And so this in pink right here, this arc length would be whatever the radius is times our change in theta, d theta. Okay, so what does that mean? That means when we're working in polar coordinates, the dA is going to turn into basically an r d theta times dr, or I kind of switched around the order. The dA is going to turn into an r dr d theta. So rather than letting our dA equal dx dy, our dA is going to be an r dr d theta. And that expression is technically supposed to represent the area of one of these kind of teeny tiny little rectangles. And we're going to let that area go to 0. We're going to have an infinite number of rectangles and then add up the heights over that region. So that's really what's happening when we're doing these integrals. Okay, so what does that mean? That means if we want to write a double integral in polar coordinates, it's going to look something like what I have on the screen. Basically, what this is saying here is we are going to take our function, we're going to get our function in terms of r and theta. And so that r cosine theta right there, r sine theta, is really just reminding us that x can be replaced with r cosine theta, y can be replaced with r sine theta. That was our polar coordinates definition. and then the dA turns into r dr d theta. It's most frequent to integrate with respect to r first and then theta second. It's just that the integrals tend to work out a little bit more nicely in that format. But you could integrate in the other order if you wanted to, using those same ideas we learned in the previous section. The concept that, okay, if you're going to integrate with respect to r first, the bounds of integration can have thetas in it. And then when you integrate with respect to theta, those numbers are going to be constant. And so if you flip the order of the integration, which I'm going to be honest, I actually never do, but you could, if you wanted to flip the order of the integration, then the thetas could be functions of r, and the r's would have to be constants. All right, so before we start doing some double integrals, I just want to do a little bit of practice of thinking about regions in polar coordinates, just kind of shifting our brain to think about what's happening in polar coordinates. So let's start by sketching the region D equals, so we have some region described by r's and thetas, and it says r is between 1 and 3, and theta is between pi over 2 and pi. So what does this exactly look like? Well, I have just drawn an r value of 1, so if r equals 1, again, what that means, r equal 1 means we have a radius or a distance from the origin of 1. So it's technically a circle with radius 1. So r equals 1 is my inside circle, and then r equals 3 just means my distance from the origin is 3, so I have a circle of radius 3. So this region is telling me the r values lie somewhere between 1 and 3, so this kind of donut shape. And then the thetas are between pi over 2, which is my 90-degree angle, and pi, which is my 180-degree angle. And so let me just shade in the region we're talking about. So we're talking about this kind of portion of this donut shape in the second quadrant. So that's the region that's been described by that r and theta. So now I'm going to describe a region in rectangular coordinates, and let's see if we can express this region in polar coordinates. Can we translate the rectangular coordinates to polar coordinates? So it says sketch the region bounded by the lines y equal x. So I'm just going to start by drawing that line y equal x. And then we've got x equal 1, x equal 4, and y equals 0. Okay, so bounded by y equals 0 is just my x-axis, and then between x equal 1 and 4. So that's the region we're talking about. I've shaded it in pink. And so now let's see if we can express this region, think about this region in polar coordinates. So to help me think about the region in polar coordinates, I'm going to think about, really, if I were drawing basically rays from the origin, how can I describe the angles made up in that region and the radiuses, or the distances, from the origin? And so the first thing I notice about the rays that I have drawn is I started by drawing a line with an angle of 0. So theta starts at 0. And then I'm going to stop up here, and the line y equals x makes a 45-degree angle with the x-axis. So I stopped at an angle of pi over 4. So this region can be comprised of angles that run between 0 and my 45-degree angle, or pi over 4. So those are my angles. Now the radiuses start at this line x equal 1 and then stop at this line x equal 4. So my r values, again, start at x equal 1. And so I'm going to take that line x equal 1, and I'm going to try to translate that into polar coordinates. So I remember that in polar coordinates, I can replace the x with an r cosine theta. So now I've got r cosine theta equals 1. And then I can even solve for r by dividing by cosine. So if r equals 1 over cosine theta, we could also write that as r equals secant theta. So my distance from the origin starts right here at x equal 1, which in polar coordinates is equivalent to r equals secant theta. And then I'm going to go ahead and do the same thing for x equal 4. That's where my distance from the origin stops, at that line x equal 4. I replace the x with r cosine theta, solve for r, I get r equals 4 secant theta. So I can describe this as a region where the r values, distance from the origin, always lies between secant theta and 4 secant theta, and the angles always go from 0 to pi over 4. And so that's how I would express this region in polar coordinates. All right, so finally, let's put this information together and see if we can convert an integral into polar coordinates and then actually evaluate or solve that integral. So we're going to try to solve the problem that I have on the screen. And the very first thing I'm going to do is sketch the region of integration. I'm going to draw the region of integration. And I think this step is really important. I don't think you can skip this step. I know graphing isn't always a popular thing to do, but I really think these are visual problems and you have to draw the picture to see what's happening, to understand what your region looks like. And that's really how you're going to convert it into polar coordinates. Okay, so I had the dy first, so that tells me my y values are between 0, so starting at y equals 0, and then stopping at this equation, y equals the square root of 1 minus x squared. And I happen to know that that equation is the top half of a circle. If you're not sure, how do I know that? I squared both sides, and then I got y equals 1 minus x squared. And then if you bring the x squared over, well, now it looks more like a circle. X squared plus y squared equals 1 is a circle with radius 1. Okay, so the first set of bounds is telling me the y values start at 0 and stop at the top half of this circle. The second set of bounds, the bounds for the x, the 0 and the 1, are telling me my x values start at 0 and stop at 1. And so technically we are just looking at the portion of this circle that's in quadrant 1. So I have drawn or shaded in the region that I'm integrating over. All right, so now I am ready to start to think about this region in polar coordinates and then translate my entire integral into polar coordinates as well. So if I think about how would I describe this region when I slice it with a bunch of rays, I notice that, well, first of all, the radiuses, the distance the points are in this region from the origin, always go from 0 to 1. We have a constant radius of 1 because we're inside this circle. So my r values always go from 0 to 1. And then for my angles, my thetas, I started at theta equals 0, and then I stopped at theta equal pi over 2. So my angles go from 0 to 90 degrees, or 0 to pi over 2. So that's important because that's going to be my bounds of integration. So I'm going to set up my integral. The r's are 0 to 1. The thetas are 0 to pi over 2. And then I'm going to translate the rest of the integral into polar coordinates as well. So the function that we're integrating is an x. That turns into r cosine theta. And then the dx dy is technically my dA. I am going to replace that with an r dr d theta. And in fact, you are always going to replace your dx dy with an r dr d theta. That goes back to kind of the beginning of this video. It's easy to forget that extra little r in there. but always replace your dy dx with an r dr d theta. All right, and so now this is something that I can integrate. Before I integrate, we might as well multiply these r's together. And so I'm going to write my integrand as r squared cosine theta dr d theta. And then I'm going to do my inside integral first, integrate with respect to r. Antiderivative of r squared is r to the third over 3. And then we still have the cosine theta. And then I'll plug in my bounds of integration. So I'll plug in the 1, plugging that in for r. Plug in the 0 and subtract them. And I end up getting a 1/3 cosine theta. I guess 1/3 cosine theta minus 0. So 1/3 cosine theta. So that's what my inside integral is. And then to finish, I now need to integrate 1/3 cosine theta d theta from 0 to pi over 2. And so my antiderivative there is 1/3 sine theta. And then I'll plug in my bounds of integration. So let's see, 1/3 sine of 90 degrees. Sine of 90 degrees is just 1. So that first term is just 1/3. And then minus 1/3 sine of 0. Sine of 0 is 0. So I'm just left with 1/3. And that's my final answer. That's the answer to this integral. Here's another one. Let's do the exact same thing. We are going to convert this integral into polar coordinates and then evaluate it. So the very first thing I have to do is sketch the region described. And I notice that the y values are going from that negative square root to that positive square root. So let's try to sketch that. And so to help me with the drawing, I think it's going to be a circle. And how do I know that? Because I have a square root and then a squared in the square root, so some type of circle. And so I've done some algebra on the screen so that I can graph this. Let me show you what I've done. So right now I'm just taking this upper bound. Y equals square root of 4x minus x squared. I squared both sides. We've got y squared equals 4x minus x squared. And then I took everything on the right side and moved it to the left. So I wrote this as x squared minus 4x plus y squared equals 0. And then to get this into a form that I can graph or that I would recognize, I had to complete the square. So I just looked at the x squared minus 4x. Half of 4 is 2. 2 squared is 4. So I added 4 to both sides. And that allowed me to write the x squared minus 4x plus 4 as x minus 2 squared. And then I have a plus y squared equals 4. And so now I can see I have a circle that's centered at the point 2, 0. And it has a radius of 2 because 2 squared is 4. All right, so lots of algebra there. And there's my picture. So I have graphed this circle centered at the point 2, 0, radius of 2. And so technically my upper bound, the positive square root, is the top half of this circle. And then the lower bound, the negative y values or negative square root, is the bottom half of the circle. Okay, but altogether, these bounds of integration are telling me that the y values are really inside this circle, between the bottom and the top of this circle. The x values go from x equals 0 to x equals 4. So we are talking about this entire circle. Okay, so the region that we're talking about is a circle. This is a great candidate for polar coordinates. So polar coordinates work really well when you're talking about things that are circles. That's kind of the most common case that I would choose to use polar coordinates if it didn't say anything in the directions. All right, so we're going to have to convert this region into polar coordinates. and then we're going to convert the rest of the integral as well. So this region, if you think about slicing it up with these rays, I'm going to start my slices down here, which is technically negative pi over 2. And then I'm going to stop my slices at positive pi over 2. So my thetas are going to go from negative 90 degrees to positive 90 degrees. Although, of course, I write that in radians. We always work in radians in our integrals. Okay, and then the r values start at 0. So touching the origin, start at 0, and they always stop at the edge of this circle. So basically, I have to take this circle right here and convert that into polar coordinates. And so there's probably a faster way to do this. Well, there definitely is. I don't know why I did it this way, but I was just looking at the circle I had written, and I replaced the x with r cosine theta and the y with r sine theta. And then I just went ahead and simplified that. So that's how I did this. I had to FOIL out the r cosine theta minus 2 squared. So I FOILed that out. That's my first 3 terms. And then the r sine theta squared I wrote as r squared sine squared theta. And that equals 4. And then the idea is we can do some simplifying. So I noticed that a couple things I can do. There's a 4 on both sides, so I could just subtract 4, get rid of that 4. And then the other thing I notice is I have a cosine squared and a sine squared. And so I can group those 2 terms together and think of that as r squared times cosine squared plus sine squared, which just turns into a 1. And so now I'm left with r squared minus 4r cosine theta. And again, I can cancel those 4's out. So r squared minus 4r cosine theta equals 0. And then I move the 4r cosine theta to the other side, divided by r. And I was actually just able to simplify this all the way down to r equals 4 cosine theta. So that circle in polar coordinates simplifies all the way down to r equals 4 cosine theta. Now, if I was clever, I could have taken my equation before I completed the square and just said, okay, well, I've got an x squared plus y squared equals 4x. And I could have right away said, oh, x squared plus y squared is r squared equals 4r cosine theta. And that would have been a much faster way to get this in polar coordinates. Regardless, I know my r values are going to go from 0 to that 4 cosine theta. Okay, so in terms of my integral then, the r values go from 0 to 4 cosine theta. The thetas go from negative pi over 2 to pi over 2. And then I'm going to convert my integral, the rest of my integral, into polar coordinates. This x squared plus y squared, I can just replace with an r squared. And then once again, the dy dx turns into an r dr d theta. So there's my integral converted into polar coordinates, and now we just have a bunch of calculus to do. I'm going to go ahead and write the r squared times r as r to the third, and then I'll integrate with respect to r first. So that r to the third becomes an r to the 4 over 4. And then I have to plug in my bounds of integration. So I'm going to plug in the 4 cosine theta and then plug in the 0 and subtract them. And I end up getting a 1/4 and then that entire quantity 4 cosine theta to the 4th. That simplifies down to 64 cosine to the 4th theta. So now I have to integrate 64 cosine to the 4th theta d theta from negative pi over 2 to pi over 2. And so I have a bunch of work written down on the screen. Hopefully this is slightly familiar from Calc 2. But if you want to integrate a trig function with an even exponent, like a sine squared or a cosine squared or cosine to the 4th, we use that power reduction identity. And so that's what I've done in pink on the right side of the screen. So I don't think I want to spend too much time on this since hopefully you learned it in Calc 2, but I can definitely clear this up during office hours or class time if what I've done isn't clear. I'll just quickly talk through it. So basically the cosine squared I can replace with a 1 plus cosine 2 theta over 2. And then I just squared that, so I used FOIL on that. Wrote it as 3 terms. And then I replaced this cosine squared at the end with that power reduction identity once again. I did some distributing, combining like terms, etc. And finally, I was able to get rid of all my exponents and get this into a form that I can integrate. So again, I just applied that power reduction identity twice to deal with that 4th power. So then I'm going to take my 64 and multiply it by what I got when I used my power reduction formula. And so I'm going to just go ahead and distribute that 64 to all of those terms at the bottom of the screen. And so I went ahead and did that. So the 1/4 times 64 turned into this 16. So again, I just took these terms, distributed the 64, copied down what I got inside my integral. All right, so now I've got to integrate 16 plus 32 cosine 2 theta plus 8 minus 8 cosine 4 theta. And we might as well combine like terms. The 16 plus 8 just turns into a 24. So that's all I did here. Oops, wrong 8. 16 plus 8 turns into a 24. Copy down the rest. And then I can integrate this one term at a time. So 24 theta, and then I get a 32 sine 2 theta over 2 minus 8 sine of 4 theta over 4. And then finally, we are almost done with this long problem. I'm going to finish by plugging in my bounds of integration. So I'm going to plug in the pi over 2 for all the thetas. And then I'll plug in the negative pi over 2 for all the thetas. And then finally subtract them. And so I did a bunch of arithmetic. And basically what happened is all of those trig values ended up turning into 0. Because sine of pi is 0, sine of 2 pi, sine of negative pi. All of those trig values turned into 0. And so I was just left with a 12 pi minus a minus 12 pi. And so in the end, 24 pi is my final answer. So this one was still quite a bit involved by switching it into polar coordinates, but believe it or not, I think it actually was a little bit easier in the polar coordinates. I think without using polar coordinates, it's likely you would have had to do a trig substitution to solve it. All right, I've got, I think, 2 more examples. So let's do 2 more examples. Let's see if we can use a double integral in polar coordinates to find the volume of a sphere with radius a. Okay, so the sphere that we're thinking about, I'll just center it at the origin. If it has a radius of a, it would have the equation x squared plus y squared plus z squared equals a squared. So that is a sphere with a radius of a. And so I want to set up a double integral that'll describe the volume of this sphere. And so what I'm going to do, because I know that the top half of the sphere and the bottom half of the sphere have the same volume, I think what I'm going to do is I'll just integrate the heights on the top half here. So I'll just integrate the heights on my top half, and then I'll just multiply that by 2, and that'll account for the bottom half of the sphere. Okay, so top and bottom have the same volume. So I'm going to integrate 2 times the z values given by that sphere over this region in the xy plane. And the region I'm talking about is the projection of that sphere, or the shadow of that sphere in the xy plane. And that slice or shadow of that sphere in the xy plane is just a circle with radius a. Okay, so first of all, let's write some of these things in polar coordinates. So my sphere, x squared plus y squared plus z squared equals a squared, in polar coordinates would become r squared plus z squared equals a squared. And all I did is just replaced the x squared plus y squared with an r squared. So that means the top half of that sphere can be written as z equals the square root of a squared minus r squared. So that's the top half of my sphere. And so that's what I'm going to be integrating. So I'm going to integrate 2 times that equation, and that'll take into account the top and the bottom of the sphere. My dA is the r dr d theta, and then I'm going to fill in my bounds of integration. So the region that I'm integrating over it is technically a circle with a radius of a. So my r values go from 0 to that radius a. And if we're going all the way around this circle, my theta values go from 0 to 2 pi. So there's the integral we're going to try to solve. So I'm going to start with my inside integral. I'm going to integrate the 2r square root of a squared minus r squared with respect to r. And this looks like a u sub problem. I'm going to let u equal the thing inside the square root, the a squared minus r squared, because then my du is a negative 2r dr, and that's going to allow me to replace the 2r dr with negative du. So this integral turns into a square root of u times negative du. That's going to become negative u to the 3/2 divided by 3/2, or negative 2/3 u to the 3/2. And then finally, I replace that u with the a squared minus r squared. And then I'm going to plug in my bounds of integration. So if I plug in the a, plugging in for r, if I plug in the a for r, let's see, a squared minus a squared is just 0. And then if I plug in 0 for r, I get 2/3 a squared to the 3/2. And so this simplifies down to 2/3, let's see, a squared to the 3/2 is going to be an a to the 3rd. So I got 2/3 a to the 3rd. That's my inside integral. And then I'm going to integrate that with respect to theta. So now I've got 2/3 a to the 3rd times theta. And then I'll plug in my bounds of integration, the 2 pi and the 0, and subtract them. And final answer, I got 4 pi over 3 times a to the 3rd. And you can look this up. This is the volume of a sphere. If you look up the formula for volume of a sphere, it is exactly that. 4/3 pi radius to the 3rd. Last example. Let's now see if we can find the volume of the solid bounded by z equals x squared plus y squared plus 3, z equals 0, and x squared plus y squared equals 1. So the first thing I'm going to do is try to draw a picture. That z equals x squared plus y squared plus 3 is a paraboloid. So the x squared plus y squared part tells me I have one of those paraboloids. And the plus 3 means it's been shifted up 3 units. So I've tried to sketch my paraboloid. And then z equals 0 is just my xy plane. So it's bounded, it looks like on the top by this paraboloid, on the bottom by my xy plane. And then that x squared plus y squared equals 1 is a cylinder. So it's basically a circle of radius 1 that continues in the z direction. So it looks like on the sides it's kind of bounded by that cylinder. X squared plus y squared equals 1. Okay, so what we're going to do is to find the volume is we're going to integrate the height. And the height of this object is given by my paraboloid, so my z values. So I'm going to integrate my height over its projection or shadow on the xy plane. And the projection or the shadow of this region is this circle right here of radius 1. So I have to integrate the z over that circle of radius 1, and that'll give me the volume of this region. So let's convert things into polar coordinates. I can replace the x squared plus y squared with an r squared. So the paraboloid becomes r squared plus 3. So the heights, the z values, oh, I just realized I wrote this down wrong. It should be an r squared plus 3, r squared plus 3. And then the dA becomes an r dr d theta. And then my bounds of integration are going to come from that projection in the xy plane, that circle. So we're integrating it over this circle. And so, bear with me, I'm going to write on here because I think I made my mistake through all of this problem. So let's see, this is a 2 right here. Okay, there we go. So my r values are going to go from 0 to 1 because we've got a circle of radius 1. We're going all the way around the circle, so the angles go from 0 to 2 pi. And so that's the integral we need to solve to find the volume of this solid. So again, to find the volume, we integrate the height, the z value, over its projection in the xy plane. So I'm going to start with my inside integral, and when I do that, I'm going to distribute the r. So I guess I have to integrate an r to the third plus 3r with respect to r. That gives me r to the fourth over 4 plus 3r squared over 2. And then I'll plug in my bounds of integration, the 0 and the 1. And so I end up getting a 1/4 plus 3/2, and then technically minus 0. So what is this? This is 1/4 plus 6/4 or 7/4. And then I'm going to integrate from 0 to 2 pi, that answer, that 7/4 with respect to theta. That gives me 7/4 theta. I plug in the 0 and the 2 pi. So 7/4 times 2 pi, and then technically minus 0. That turns into 7 pi over 2. And there's my final answer. There's the volume of that object. All right, that was the last example. As always, let me know if there's anything I can clear up from these problems.